Welcome back, viewers. In this class, we are going to be looking at series resistive circuits. So that is what we have here. So when we are talking about series resistive circuits, we are talking about the pattern in which resistors can be arranged in a circuit. So we have two patterns that we mostly talk about in electrical circuit. So which is the series pattern and the parallel pattern. So although we already know that an electric circuit is the combination of any number of sources and loads connected in any manner that allows charge to flow. So you can also see is the part made by connecting some components together for the purpose of what flow of current. So any which way it is acceptable. The electric circuit may be simple, such as the one you have in your battery, and you connect it with light bulb. Let's say, for example, in a case like this, one we have here. So this is known as a closed loop circuit. So let's say this is the direction of the conventional current. This I, this is the direction of the conventional current. So this is the source and this is the load. So this is an example of a simple circuit. So it may be as simple as this, which is when we have a battery connect to a load or a resistor directly. So it may be as simple as this, or in some other case, it may be a circuit may be complex, such as the one we normally have in our computer, in our television set, and some electronics we have at home. So and also we can talk about others like the microwave oven and our computer and our cell phone and so on and so forth. So we can have all these one are known as a in all this one we can find a complex circuit. So let's quickly name this one simple circuit. So in another way it is called a closed loop circuit. So a closed loop circuit. So that's another name for it. So, however, no matter how complicated, each circuit follows what we call fairly simple rules in a predictable manner. So, once these rules are understood, any circuit may be analyzed to determine the operation under various conditions. So, so there are rules that guide this, no matter which pattern, no matter how complicated or tough a particular circuit looks. So there is always a pattern which we can approach them so that we can be able to analyze them. So in this a series circuit where we normally in this circuit now is a simple series circuit, so which we normally make use of what we could known as what uh, anything that has to do with our series pattern. We use a series approach to attempt them. So let's say, for example, the use of Ohm's law as the basics and the use of Kirchhoff's voltage law. So these are the laws and the rules we normally use to approach any question or any circuit that is in form of a series. In short, we can say two elements are said to be in series if they are connected at a single point and if there are no other currents carrying connections at this point. So that is the simple understanding of a series circuit. So a series circuit is also the simplest form of circuit. It has all its elements connected in one loop of wire. So this is what we call one loop or a single loop of wire. So that is the single pattern that it follows. So now let's go a little bit higher. So the figure we have here is a simple electrical circuit. So which has three resistors, or we can call it a light bulb. So these are the things we are going to note in this circuit. So number one thing is what the current is the same through all the three conductors. So no matter what, in any series circuit connections or series network, the current that flows through each conductors or or load is going to be the same. So which means, let's say for example, if an ammeter is connected behind each of these resistors now, or behind this each of these lamp, and you switch on the power from this place, you supply the current through this place, so the same current is going to read on this ampere. So that is what we mean by that. The second one, voltage drop across each is different due to its different resistance, and this is given by Ohm's law. So what do we mean? So the resistor here might be different from this one, might be different from this one as well. So no matter what, the voltage, it will be will be different as well. So which means uh, if the resistor is high, the voltage is going to drop by the amount of the resistor that we have on each unit of this circuit. So that is what we mean, and this is due to the what the difference in resistance, and is given by the Ohm's law according to what we have here. So the last but not the least is the sum of the three voltage drop is equal to the voltage applied across the three conductors. I think this has been taken care of in our what do you call it, Kirchhoff's voltage laws topic. So which means the voltage that rises from this point is going, no matter what, is going to be equivalent to the sum of all the voltage that drop across these components. So that is what that the last one is all about. So now, and a series resistive circuit can appear in different forms. So it's not necessary for it to be in a closed loop circuit like this. It can also be in a straight chain. It can be in a zigzag manner. It can be in any form. So in as much that we are having two nodes, which is at the beginning and also at the end. So let's say look at this one. We have a crosswire there, but it doesn't mean it is joined together. So this is an example of all these are examples of a series resistive circuit. So what does this mean? It means as long as the circuit elements are connected one after the other, just like we have them like this, as long as they are connected one after the other. So and there is only one current um, path. So this is just the single current path that we have there. And when there is only one current path, it is said that they are connected in series. As simple as that. That is the so it does not matter if there is a different arrangement of the element, if it is in this form, or whether it is so seen, as long as it's just single path that the current flows through. So it is said to be in a series circuit. So now, away from the pattern of series circuits, so let's look at the main thing that is inside it. How do we analyze all these things? So what we are going to be taking first now is what we know as a total series voltage, which we know as VT um or E. So when we are talking about the total voltage in a series circuit, so we look at it from this angle. The voltage across the source, which is the source here, or power supply, is equal to the sum of the voltage that drops across each resistor in a series circuit. So that is uh, the source voltage shared by each resistor. So the terminal of this resistor connecting into the positive side of the voltage source is positive, and the terminal of the resistor connecting to the negative side of the voltage is also negative. So this is a positive to positive, and this negative to negative on the other side. So how do we deal with this? So we deal with this. The total voltage in the circuit can be determined by using what we know as a Kirchhoff's voltage law. So which, and on Ohm's law as well, which we have already treated in one of our topics. So, and how do we do that? We easily say that VT which is the same thing as our E is going to be equal to V1 plus V2 plus V3. So, and even though we have the infinity, we are going to state them. So that is the law that guides uh, the total series voltage in a series circuit. So, and we can say our VT from this place is the same thing as I. So from VIR1 plus IR2, so to whatsoever I, so VN IRN, which is the same thing as IRT. So basic understanding of uh, that's the basic understanding of a total series voltage. So another thing as well is the total series resistance. The total series resistance. So whenever you come across resistors in a series circuit, the same thing, the total series resistance are going to be added as well, which means the total the series resistance in a series circuit is what is they are additive. So the voltage are addictive, the resistors are addictive, even the power as well are addictive. So this can also be carried out by the what we know as the Kirchhoff's voltage law as well. So the total series resistance in a series circuit as well is also addictive, which means our it can be called total series resistance, or it is known as an equivalent resistance. So RT, or you call it REQ, so which is known as equivalent resistance, which is the same as R1 plus R2 plus T. Uh, no matter how long it is, or the numbers of resistors connected in it. So the last one, or the next one we're going to be, we can also have series current. What happened to the current that is in a series circuit? So, from as I. So from the beginning, we said that when we are talking about the definition of a series circuit, we said um, uh, that there is only one part in which current flows through in a series circuit. So, which means the current flowing through each element is always the same, and the current is always the same at any point in a series circuit. So the current flowing in a series resistive circuit, such as the one we have in that what do you call it, in that figure we have here, so it's always the same. So our high is going to be Vt over Rt, so which is the total resistance, total voltage, total series voltage over total series resistance, which is still the same thing as E over RT. So it's the same thing as the one we are going to have in the first component, and it's still going to be the same thing with the one we are going to have in the second component, like that, till infinity, or till whatsoever the number you have next, to the end of this connection. So, and the last but not least we can find is series power in a series circuit. We have series power in a series circuit as well. So in the case of series power as well, each of the resistors in a series circuit consume power as well, so which is dissipated in the form of heat. So the total power, known as PT, equals IE IV1 IV2 till whatsoever number you are having. The same thing is applicable. PT is equal to 1 P1 plus P2 plus P3 to the rest. We can also have it to PT equal to IE, so which is also known as the VT, the total voltage in series, which is equal to what the power, which is I square RT. If you can recall to our the topic under our energy and power, so which is also can be regarded as E square over RT. It can also be regarded as a VT square over RT. So we can have them as follows as well. The power dissipated by the individual resistor in a series resistive circuit as P1, P2, or P2 whatsoever as I square Rn, which is equal to IVN is equal to Vn square over Rn. So this is the analysis of component, be it total voltage in series, total resistance in series, total current in series, total power in series. So this is the analysis and how they can be executed in a what, in a series circuit. So from all this now, we can deduct the characteristics or properties of a series circuit generally. So which is going to be given as this. So we can say the same current flows through all parts of the circuit. So if you look at the O shape, the same current that flows through it. Different resistors have their individual voltage drops. Voltage drops are additive. Apply voltage equals the sum of the different voltage drops. Resistance are also addictive, power are also addictive, and don't forget current are also addictive. No, the current is also are the same through all the components, through all the part of the circuit. So uh, before we round up, let's quickly take a look at some illustration we have here. So let's take a look at this question that we have here. A series resistive circuit in the figure below. In the figure, this is the figure. Determine the following. We have total resistance RT, current I in the circuit, voltage across the resistor R1. I think that's R1. Total voltage VT, and the last but not the least, the total power PT. So let's take them one after the other. So let's have it solution. Solution. So number one, so our question here says that we should find the total resistance R2. So we can also regard this as the equivalent resistance. We should come back here when we say we are talking about the total resistance in a series circuit. It's going to be R2 REQ to be R1 plus R2 T whatsoever number of resistors you have in this circuit. So we are going to, how many resistors we have here? We have just three resistors. So our RT is definitely going to be our R1 plus R2 plus R3, as simple as that, which is going to be, by the time we substitute all this thing, we're going to have 10 plus 20 plus uh, 30. So everything altogether is going to be 60 kilo ohms. So I think everything is in kilo ohms. So that is what we're going to have. So the question B there. So we have been told to find the current in the circuit. So if you are going to find the current in the circuit, we have been told that the current in a resistive and a series circuit is always the same throughout whatsoever might be the unit of the circuit. So which means we are taking use of this. We are making use of this. So uh, which says, let's take a look at this one. So which says what, the current which is I is equal to P over RT, and this is our RT, and our E, according to what we have in the circuit, is going to be 60 voltage, and our what do you call it, our total resistance is 60 kilo ohm, which is 50 equivalent to 60,000. So by the time we divide this thing, we are going to have the six we cancel each other out. We are going to have one. So this is, since we're having this, and 60 will be one, so we're going to have uh 1 milliamp, so as not to waste our time on that. So the next thing we are going to be looking at is the third one, which is C. Our question C, we have we should look for voltage across the resistor R1. So if you look at this voltage, where is this? Yes, voltage across any resistors R1. So it's going to be um, V. From Ohm's law, we have V is equal to what? I R, and we know the value of our R. So the the same thing is so it's going to applicable to the one we are looking for, which is V across what um, R1, which is V1, is going to be I um, I sorry I R1. So IR1. So definitely it's going to be what's our high, which is 1 milliamp, 1 milliamp. So multiply by our R1, which is what? Which is equivalent to 10 kilo ohm. 10 kilo ohm. So if you punch your calculator, I believe this is equivalent to, uh, I think it's going to be 0.001 um, times 10,000, which is the same thing as 1 times 10 raised to power minus 3, if you can see it, which is 10 raised to power 3. So at the end of the day, we are going to have the voltage V1. So V1 is going to be, we're going to have 10 left. So we're going to have 10 volts. So that is what we're going to be having there. So without wasting much of our time, the next one we're going to be looking at is our D question D. Our question D says we should look for the total voltage. So if we have apply our law, our Kirchhoff's voltage law, so to look for this, we are going to have our and the sum, we said the sum of the voltage that rises from the power supply is equal to the one that drop across the uh, along the, what do you call it, along the series circuit. So which is going to be what? Our V, our VT. So which is the same thing as our RT is going to be um, one one sorry, it's going to be 1 milliamp, 1 milliamp. So times RT. What's our RT? Our RT is what? Is 60 kilo ohm. So I think that is what we are going to have from this. If that is to look for the total voltage. So that is what we have here. So we pick it out from this side. So which is going to be simply 60 uh, voltage. So of course it is correct because it's the same thing as what we have as the supply voltage there. So the last but not the least, the last question, which is question E, which has to do with the total power. So and in looking for our total power PT. So from what we have here, so we can pick any of these things. See that we have PT to be high E or any of this. So let's pick IE so that we won't waste much of our time. So let's pick IE. So our PT is IE. So which is the same thing as what's our high? Our high is 1 milliamp multiplied by our E. What is the total? Our E is total voltage, which is 60 volts. 60 volts. So and finally the PT we are going to be having there. This one is not going to change. We are going to be having 60 times 1, that is 60 milliwatts. So that is the final answer. And on that note, we have come to the end of this lesson. Please, you are free to lay any your post any comments. We will reply you. If there's any question you want us to treat together, you can send it to our email onlineseries@gmail.com. You can please help us to like, share, and subscribe to our YouTube channel so that you can enjoy more of our videos. Thank you for watching. We shall see you in the next class. Bye.